About 4 billion years ago, something roughly the size of a small protoplanet slammed into the moon with enough force to gouge out a scar nearly a quarter of the way around its entire circumference. That scar is called the South Pole Aitken Basin, the largest and oldest confirmed impact crater anywhere in the solar system, sitting quietly on the moon's far side for billions of years, since largely hidden from Earth-based observation simply because of where it happens to be located. In June of this year, 2 new studies revealed something about that ancient impact that carries a genuinely remarkable implication for NASA's current plans. Plans that are not some distant, hypothetical future mission, but a specific, funded program with real astronauts training for it right now. The collision was so violent that it appears to have blasted material up from deep inside the moon itself, from its mantle, the thick, rocky layer sitting directly beneath the thin outer crust, scattering some of that deep material across the surface of the exact region where NASA's Artemis astronauts are currently scheduled to land. This is the story of what those studies actually found, why a piece of rock from inside the moon would be one of the most scientifically significant objects any human being has ever held, and why the answer to one of planetary science's oldest, most foundational questions might be sitting right now, somewhere within walking distance of where the next astronauts to reach the lunar surface are actually planning to go. To understand why this discovery matters so much, you first need to understand exactly what scientists mean when they talk about a planet's mantle, and why getting an actual piece of one has proven so difficult for as long as planetary science has existed as a field. Rocky worlds like the Moon, Earth, Mars, and Mercury did not form as simple, uniform balls of material. In their earliest history, while still partially or fully molten, heavier elements sank toward the center of each of these bodies, while lighter material rose toward the surface, a process called differentiation that sorted each world into distinct layers, a dense metallic core, a thick intermediate mantle, and a thin outer crust. For the moon specifically, this process is described by what scientists call the lunar magma ocean hypothesis, the idea that the moon, shortly after its formation, was entirely or nearly entirely molten. A genuine ocean of liquid rock covering the entire body, which then slowly cooled and crystallized over time, with different minerals solidifying and settling into layers in a specific, predictable sequence as the temperature dropped. This same basic differentiation process is thought to have shaped nearly every rocky body of significant size in our solar system, and understanding exactly how it played out on any one of them offers a window into how all of them, including our own planet, actually came to be built the way they are. The problem is that a planet's mantle, by definition, sits buried beneath its crust, often at depths far beyond anything humans have ever been able to physically reach. On Earth, the deepest hole ever drilled, the Kola Superdeep borehole in Russia, reached a little over 7.5 miles down after nearly 2 decades of continuous drilling effort. And Earth's mantle begins at depths far greater than that across most of the planet, meaning even that extraordinary engineering achievement never came remotely close to reaching mantle material directly. On the moon, the challenge is different but no less severe. The lunar crust varies dramatically in thickness from one region to another, thinner beneath the near side's dark volcanic plains, and considerably thicker beneath much of the far side highlands. And reaching the mantle directly beneath it would require either an extraordinarily deep drilling operation far beyond anything current lunar missions are equipped to attempt, or a naturally occurring event violent enough to do that excavation work for us, bringing mantle material up to the surface where astronauts or robotic missions could simply pick it up without digging at all. That is exactly what scientists studying the South Pole Aitken Basin now believe happened roughly 4 billion years ago in a single catastrophic collision. 2 new companion studies, one published in the journal Science Advances and one in the Journal of Geophysical Research. Planets, both led by researchers at the Center for Lunar Origin, and Evolution, a NASA-affiliated research group based at the Southwest Research Institute, worked together to reconstruct exactly how that ancient impact unfolded, and what it likely did to the material sitting beneath the moon's surface at the time. The first study used detailed hydrocode computer simulations, a kind of modeling that lets researchers recreate the physics of an extremely violent high-speed collision in careful mathematical detail, testing different scenarios for the size, angle, and internal structure of whatever object actually struck the moon to create this specific basin. Hydrocode modeling works by treating the colliding bodies as fluids under the kind of extraordinary pressures and temperatures generated during a hypervelocity impact. Since at the speeds involved in an event like this, solid rock behaves, for a brief violent instant, much more like a liquid than anything resembling ordinary stone, allowing researchers to simulate exactly how material would flow, fracture, and get thrown outward under a wide range of different possible impact conditions. The team, led by researchers, including Shigeru Wakita and Brandon Johnson, found that the distinctive, elongated, tapered shape of the South Pole Aitken Basin, a shape that had puzzled researchers for years, since a simple head-on impact tends to produce a far more circular crater, could only be reproduced in their simulations under one specific set of conditions. The impactor, the team concluded, had to have been a differentiated object in its own right, meaning it had already undergone its own internal layering process, its own core and mantle already separated, before it ever struck the moon, and it had to have hit at a shallow angle, arriving from the north and traveling on a path angled toward the south, rather than coming straight down. Only that specific combination, a pre-differentiated impactor striking at a shallow southward angle, produced a simulated basin shape that actually matched the real elongated scar visible on the moon today, published in the journal Science Advances in May of this year. The second study approached the same basin from a completely different angle, quite literally, using gravity data. NASA's Grail mission, which flew two small spacecraft nicknamed Ebb and Flow in tandem orbit around the moon, specifically to map tiny variations in its gravitational field, had already produced detailed data revealing subtle differences in density across different regions of the lunar subsurface, differences too small to see with an ordinary camera but detectable through their gravitational effects. Since denser material pulls slightly harder on a passing spacecraft than lighter material does, a difference the twin Grail probes could measure by tracking minute changes in the distance between themselves as they orbited in formation. Combining that Grail gravity data with laser altimeter measurements of the moon's surface topography from NASA's Lunar Reconnaissance Orbiter, the research team, led by Gabriel Gauman alongside several of the same researchers involved in the first study, built detailed models of the density structure lying beneath the South Pole Aitken Basin and the wide apron of ejected material surrounding it. What they found was a substantial signature consistent with mantle-derived rock, material denser, and chemically distinct from ordinary crust. Embedded both within the basin itself and mixed throughout the debris field, blasted outward across the surrounding surface when the original impact occurred, a finding published in the Journal of Geophysical Research. Planets. Put those two studies together and a specific, remarkable picture emerges. An ancient, already differentiated object struck the moon at a shallow angle roughly 4 billion years ago, gouging out the largest crater in the solar system, and, in the same violent instant, excavating material from the moon's own mantle and flinging it outward across the surface, mixed into the debris field surrounding the impact site. That debris field, according to the gravity modeling in the second study, is not confined to some remote, inaccessible stretch of the lunar far side. Significant portions of it overlap directly with the lunar south polar region currently being considered, and in some cases already selected, as landing territory for NASA's upcoming Artemis missions, including the sites currently planned for Artemis 4. William Botka, director of the Center for Lunar Origin and Evolution and a co-author on both studies, described the basin directly as offering scientists a genuinely rare opportunity to study the moon's earliest history, a chance that exists specifically because of how violently and how deeply that ancient collision tore into the lunar interior. He also described the value of combining both research approaches together, explaining that pairing detailed impact modeling with careful gravity mapping gives researchers something closer to an actual roadmap, not only reconstructing how the South Pole Aitken Basin actually formed in the first place, but pointing towards specific locations where the rocks capable of answering some of the biggest remaining questions about the moon's origin and evolution might actually be sitting today, within reach of a mission that is already planned and already funded. If Artemis astronauts do manage to identify and collect a genuine, confirmed sample of lunar mantle material during a future South Pole mission, the scientific value of that single rock would be difficult to overstate. It would represent the first confirmed piece of the lunar mantle ever directly examined by human beings, something that has eluded planetary science for more than half a century of lunar exploration. Through every Apollo mission, every robotic lander, and every orbital survey conducted since humans first walked on the moon in 1969, the Apollo missions returned more than 800 pounds of lunar material combined, an enormous scientific windfall that reshaped our understanding of the moon's crust and surface history. But every single one of those samples came from the crust, the outermost layer, never from the mantle sitting beneath it, simply because none of the Apollo landing sites happened to sit near a feature capable of excavating material from that far down. More specifically, a confirmed mantle rock would offer the first direct observational test of key predictions made by the lunar magma ocean hypothesis, a model that has been built almost entirely on indirect evidence, remote spectroscopy, gravity data, and theoretical modeling, rather than on an actual confirmed sample of the deep material the theory describes. A genuine mantle rock could directly test specific predictions the model makes about mineral composition deep inside the moon, including whether the lower mantle is dominated by a specific mineral called magnesian olivine, crystallized in a particular sequence as the ancient magma ocean cooled, and how much that original sequence was later disrupted by gravitational overturning, a process where denser crystallized material sinks while lighter material continues rising. as denser and lighter minerals continued shifting position deep beneath the surface, long after the moon's crust had already solidified on top. Testing that specific prediction against an actual physical sample, rather than an inference built entirely from indirect measurements taken from orbit, would settle a question about the moon's interior that has remained genuinely open for the entire history of lunar science. The implications of a confirmed answer here would not stay confined to the moon, either. The same basic differentiation process, molten material sorting itself into a core, a mantle, and a crust, is thought to have shaped every rocky body of significant size in our solar system, including Earth itself, along with Mars and Mercury. A direct physical test of how that process actually played out on the moon, using an actual sample rather than an indirect inference, would give planetary scientists a genuine, independent benchmark to compare against differentiation models built for these other worlds as well, models that, for Mars and Mercury in particular, remain almost entirely theoretical, built without any confirmed mantle sample from either planet ever having been directly examined. In a very real sense, a single rock picked up near the moon's south pole could end up refining our understanding of how Earth itself came to be layered the way it is, simply because the underlying physics connecting all of these worlds together is fundamentally the same. None of this guarantees success, and the researchers involved have been careful consistently to frame their findings as identifying where the right material is most likely to be found, rather than promising astronauts will simply stumble across a perfectly identifiable mantle rock sitting in plain view. Confirmed mantle material is expected to exist at what researchers describe as a trace level within the regions currently being considered for Artemis landings, mixed in among far larger quantities of ordinary crustal material, ejecta, and the kind of heavily processed, repeatedly impacted regolith that covers essentially the entire lunar surface after billions of years of accumulated micrometeorite bombardment. Identifying a genuine piece of mantle material among all of that surrounding material will likely require exactly the kind of careful, trained, in-person geological judgment that no robotic sampling mission, working from a fixed set of pre-programmed instructions, could easily replicate on its own the same basic argument for the scientific value of human explorers, rather than robots alone, that has run through NASA's justification for returning astronauts to the lunar surface at all. That is precisely why this discovery lands with such specific weight right now, at this particular moment. This is not an abandoned scientific curiosity waiting for some hypothetical future mission decades away to eventually investigate. The exact region these two new studies identify as the most likely location for confirmed lunar mantle material overlaps directly with landing sites NASA has already selected, or is actively finalizing, for the Artemis program's return to the lunar surface. A mission with a specific, real, currently scheduled target rather than a distant, undated aspiration. Astronauts could plausibly be standing in the middle of this exact debris field within the next few years, equipped for the first time in the history of lunar exploration. With a specific scientific target, and a specific reason to look closely at exactly the kind of rock that could finally answer a question planetary scientists have been trying to test directly, since long before any human being had ever set foot on the moon at all. If this is the kind of story you want more of, subscribe, and let me know in the comments whether you think Artemis astronauts will actually manage to bring one of these mantle rocks home.